Hello. Let's go through the third chapter of statistics, representations of data. In this video, we'll be looking at what an outlier is and finding different methods to calculate outliers in a dataset. Let's begin with a definition. An outlier is an extreme value that lies outside the overall pattern of the data. We're going to see there are two types of outliers, values that are too big and outlier values that are too small. Sometimes they are legitimate values. However, on some occasions, outliers occur due to experimental or recording errors, which is called anomalies, and they should be removed from the dataset as it would be otherwise misleading. This process is called cleaning the data. So in this video, you should be comfortable using two methods to calculate outliers. Method 1 uses a formula based on quartiles and the interquartile range. Specifically, a value x in a dataset is said to be an outlier if it satisfies either of the inequalities. The lower outliers would be given by this formula here if the value is below the lower quartile subtracted some multiple of the interquartile range. And we've got a similar formula for the upper quartile plus some multiple of the interquartile range. We'll see this value of k will often be 1.5, but it can vary depending on different data sets. But in an exam, it will always be stated in the question. So we would often use this method for calculating outliers for non-symmetrical data. A real-life example might be the wage distribution in the UK. Often you'll see in government statistics the median and quartiles being used to represent this data. We will also learn a second method for calculating outliers, and this one will be based on the mean and standard deviation. In particular, a value in a data set will be said to be an outlier if it lies some multiple away from the mean of a standard deviation. Again, that multiple A can be 2, but will often change depending on the context. But again, in an exam situation, it will always be stated in the question. So we'll use a method based on the mean and standard deviation in more situations where the data is symmetrical. And an example of that might be the heights of various different animals in their particular species. We often assume that's a symmetrical distribution. Okay, so we've got some formulas there, but we would like to understand a bit more by doing some specific examples. Let's have a look at question 1. The blood glucose of 30 females is recorded. The results in millimoles per litre are shown below, and we can see the data set. An outlier is an observation that falls either 1.5 interquartile ranges above the upper quartile, these will be our upper outliers, or 1.5 interquartile ranges below the lower quartile, and these will be our lower outliers. Okay. Part A asks us to find the quartiles. We will recall that the formula for the lower quartile, Q1, is n over 4 data points. In this case, n is the number of data points, so n would be 30. So we're looking for 30 divided by 4 equals 7.5 data points. And I'll remind you that we round up when we find quartiles. So we're looking for the 8th value. 1, 2, 3, 4, 5, 6, 7, 8. So Q1. Oops, messy handwriting. The lower quartile is 3.2. In a similar way, we can find the upper quartile, Q3, the 3n over 4th data point, which in this case would be the 20.5th data point. And again, we round up to the 23rd value. So that would be 30th, 29, 28, 27, 26, 25, 24, 23. So the upper quartile is 4.0. Now in part B, we're going to use those values to find the outliers. So we're going to split this into two halves. We're going to find the upper outliers first. So we'll think about the upper outliers. Are there any values that are too big in that data set? Well, our formula is 1.5 interquartile ranges above the upper quartile. In particular, Q3 plus 1.5 times the interquartile range. So I can see it's going to be necessary to work out the interquartile range here. So let's take a second to do that. The interquartile range is upper minus lower quartile, which in this case is 0.8. So I think we're now ready to substitute into that red formula. That gives us the upper outlier boundary. So 4.0 plus 1.5 times 0.8. Doing the maths comes out to an upper boundary of 5.2. And when we look back at the data set, we can see there are no values that exceed the value 5.2. So we can say confidently there are no upper outliers. And now we need to find out, are there any lower outliers? Well, it's a very similar formula to find out if there are any lower outliers. We are looking 1.5 interquartile ranges below the lower quartile. So that would be Q1 minus 1.5 times the interquartile range, which in this case would be 3.2 minus 1.5 times 0.8. And again, doing the arithmetic gives us a cutoff of 2.0. And if we look at our data set, we can in fact see that we would get an outlier of 1.7. So we can say 1.7 is indeed an outlier. Okay. So after solving the question, let's reflect on how we did it. Well, we had to use two formulas to find the upper and lower boundaries. We found that there were no upper quartiles. In fact, there might not be any outliers in the whole data set, but in this case, we were able to find one outlier on the lower side of things. Okay, let's move on to question 2. In question 2, we're going to be having a look at a different method of finding outliers using mean and standard deviation. Let's read the question. The lengths in centimetres of 12 giant African land snails are given below. And there's the data set. We would like to calculate the mean and standard deviation given those formulas. Okay, well, let's recall two formulas. The first we have to learn off by heart that x bar is the sum of all the x values divided by the size of the data, the number of data points n. The second formula is given in our formula book. The standard deviation sigma is the square root of sigma x squared over n minus the mean squared, square rooted. Okay, let's now substitute those values in and get some numerical values. So x bar would be 252 over 12, so the mean is 21 centimetres. And let's substitute into the standard deviation formula. The sum of all the values squared, sigma x squared, we are told is 5468. Again, there are 12 data points, and we can now substitute in the mean for 21. And then working out that value, we get sigma equals 3.83 to 3 significant figures. Okay. And now we'll be able to see how we can use these summary statistics to find any outliers. In part B, we're told that an outlier is an observation which lies 2 or more standard deviations from the mean. And it's our task to find any outliers for this data. In a similar way to last time, I'm going to be looking for a lower boundary. So that means I'm going to start at the mean, x bar, and I'm going to take away 2 standard deviations to get a lower boundary for outliers. Substituting the values, 21 minus 2 times 3.83 gives a lower boundary cutoff of 13.34. And then when I look back at the data set, I can see there are no lower outliers. There are no values less than 13.34. No lower outliers. No value was too extremely small to consider an outlier for this data set. And then in a similar way, let's find out the upper boundary. And it's a similar calculation, but this time we want an upper boundary. So we'll look at x bar plus 2 standard deviations. Doing the arithmetic, 21 plus 3 times 3.83 and so on. And we'll get a cutoff value of 28.66. And if we refer to the data set, we can see our cutoff value means that 32 is an upper outlier. And indeed, we can write a conclusion that 32 is an outlier. In fact, it's the only outlier of this data set. Okay, so that concludes our first video. I would strongly encourage you now to practice exercise 3A to see if you can use the formulas that we talked about at the start.